Okay. So this is a self-study class for two courses, NTMI and NLP1. So this is a 2023 edition. It's an introduction to probabilistic graphical models, in particular to directed graphical models, or Bayesian networks as they are also known. The outline and goals are as you can see here. So you should use this material to help you in your self-study time. It is a very introductory class. If you want to know much more about graphical models, then this is a textbook reference for you. I will motivate the topic from an NLP point of view and then discuss it in some generality. And here you have some of the learning goals. You can take a moment to go through them. As you go through the material, if you notice that you could use a recap of probability theory and statistics, then I'm linking two sources, some lecture notes that you can find here, and a Jupyter notebook that you can find here. But any undergraduate text on probability and statistics would do, including, material you find online, maybe video lectures you can find online. All right, so what is the problem? The problem is that in NLP, we typically design probability models, models that specify or prescribe probability distributions over structured data. And examples of structured data are documents, trees, and graphs. The problem with that is that typically the sample space, so the space of all objects you would like to be able to assign probability to, are typically too large in NLP. So here, for example, the number of possible syntactic trees for any one sentence grows exponentially with sentence length. So I'm showing you that as you bracket things differently, you get alternative objects. And I've only shown you 3 of them, but you can imagine that by changing these word categories and phrase categories and changing how these binary brackets are, these binary branches group them going bottom up, you will find many alternative objects. And they're not all correct, clearly. And that's part of the point of designing probability models. We want these models to distribute probability mass in a way that is useful. This space, in fact, grows much faster than the sentence themselves. So if I grow the sentence by 1 extra word, you will see that there will be many more possible trees. So this exponential growth is part of the problem. Sometimes the sample spaces are actually infinite, or you cannot easily bound it. So for example, there's no real obvious limit to how many different ways I could write about a sentiment. So here I'm showing you a few very short sentences. What a great day, which might be positive, negative, or neutral, might express one of these 3 types of sentiment. What a strange day, what a busy day, and it goes on, right? And these sentences can vary in length, in topic. I really could not possibly put a limit to this. So this space is infinite. So this causes a problem because it's a consequence of either being too large or being infinitely large. We cannot really represent a joint probability distribution over all of the outcomes by simply storing one probability value for each possible outcome. Not only we might not be able to store those things, probability values come from somewhere, typically not from our imagination. We typically obtain them by optimizing some criterion, some statistical criterion, using data. And I've never heard of anyone who has access to infinite data. Definitely you have only finite time in your life. So mostly you're going to be working with finitely many observations. And if you were to then have to bootstrap infinitely many probability values, that seems like a very challenging thing to do. So this is the problem. We are dealing with spaces that are much too large for us to specify probability distributions in sort of oversimplistic ways, assigning one probability for each possible outcome in this space. What's the solution? So the solution that we are going to talk about in this class is that we're going to use knowledge of the application domain and motivate some simplifying assumptions. And these assumptions will make our distribution simpler, or at least it's going to be more feasible to specify them. The key to the whole thing is that we'll be computing the probabilities of the objects we care about by essentially manipulating a finite and hopefully small, if possible, number of elementary probability factors. So you still want to be able to assign probability to as many outcomes as you have in the sample space, exponentially many or infinitely many. But you want to express the probability of every single outcome using something that is finite, hopefully small. So it's a kind of a decomposition problem, right? You're going to decompose an object into others. I want to give you an intuition, and it's just an intuition. Don't take this metaphor too seriously. But think about when you learned how to factorize natural numbers using prime numbers. So if I would give you a number like 24, you were told you could decompose it into 2 times 2 times 2 times 3. And those numbers, 2 and 3, they are special, and we call them prime numbers, in that they are not further decomposable, right? So they are elementary in some sense. The idea is very similar. Look at this. So factorizing into primes essentially allows us to express all composite, and composite is the word I'm using here for non-prime numbers, by multiplying together some prime numbers. So for any large but finite subset of the natural line, so let's say you think of some very large natural number m, and then you think of all numbers between 1 and m, there are far fewer prime numbers in that interval than m itself, than the composite numbers in it. So we get to represent a very large set by only knowing a small collection of numbers. Those are the prime numbers. And when we see a composite number, we can think of it as, well, we're not really seeing 24. We are seeing 2 times 2 times 2 times 3. And with some computation, we can express the actual number 24 if we want. We can evaluate the actual number 24 if we like. Factorization into primes is an algorithm that reviews a construct of this form, a decomposition into some elementary things, elementary objects. We're going to be doing something more or less like it for probabilities. So we decompose the probability of something which is complex. And by complex, let's say it's at least decomposable into parts. And of course, the vocabulary of parts is kind of a parameter of this algorithm. You're going to have to decide what the parts are. Into a product of probability of simpler things. So for example, here I have a syntactic tree, and I'm going to treat the tree as a composite object, and it's made of context-free tree fragments. And I can express the probability of the composite thing as a product of probabilities for the elementary parts. And you see that these elementary parts can probably be recomposed differently as to make another composite object. So this is a bit different from factorization into primes, which is kind of, it's unique, right? 24 gives you have a set of parts, and that set of parts can only make 24. Here, things might be a bit different. I have another example here where I have a labeled document, and I'm decomposing it into labeled word pairs. And to give you an idea of word pairs, I made it as if the parts would plug like a jigsaw puzzle. So it's a similar notion with a few important differences, and we get to decide what the parts are, the elementary parts are. We're going to call these parts factors. And we are going to figure out ways to express these things, these decompositions, and ways to manipulate them as to be able to express every probability of interest. I'm going to be using a lot of notation, so you pause the video now and you read it very carefully, and you just refer back to this slide whenever you are slightly confused about some notation, or you ask a question afterwards. I think now I'm going to just very briefly mention a few things. I'm going to be using uppercase letters for random variables, like these ones, and lowercase letters for their outcomes. If I ever use a calligraphic letter, I mean the range of the random variable, so the possible outcomes. If I ever use this omega, I mean the sample space. So the underlying sample space is something like the words or the sentence or the documents. And typically when you implement, you remember that if you ever implemented an NLP model, you have some sort of dictionary mapping words to numbers, because natural numbers are easier to manipulate, as token IDs. So the numbers, the IDs, are kind of the range, and the underlying vocabulary of actual words, that's the sample space. An assignment is denoted like this. The big letter is assigned the small one, and what this really does is it instantiates an event. And an event is basically a subset of the sample space. If we ever pronounce this in English, we can just say the random variable takes on the value x in its range. For convenience, in this class and in much of NLP and in much of the literature, we do not really distinguish the sample space and the range. It's kind of an unnecessary, it's a necessary, but it's a necessary formality that is not dangerous if we skip. Especially when we deal with discrete random variables. So I'll just trust that you can imagine the mapping, from token to token IDs in your, you can imagine that. I don't need to specify that for you. It's kind of like an implementation detail that I leave to you. I use this notation to denote the probability of x taking on, big X taking on small x. You can see why. This is a bit shorter when you typeset in LaTeX than that. And I also do that for multiple variables, okay? So this is kind of this is maybe the more familiar thing, and this is the shorthand. And you see that it does save me 50% of the space, I think. If I ever refer to the distribution of x in text, I might write it like this, px, see, without any argument. So that's the entire distribution. And I do that for any other type of random variable combination. So here you have the joint distribution of x and y. Here you have the conditional distribution of y given an outcome of x. Okay, and then sometimes if I want to mean the collection of all possible conditional distributions for all possible values x may take on, maybe I write it this way. Again, you forget the things, no problem. Do you see that it grows in you? It's fairly intuitive as you start using it, but don't try to memorize it all at once. Whenever you encounter the symbol, if in context the symbol isn't clear to you, go back to this slide, you'll find the explanation. All right. Okay, let's get to the class. So factorization of probabilities, the very first tool you were probably exposed to before this course was the chain rule of probabilities. So to factorize, to break into parts, and to factorize a joint probability like PAB, we could, for example, use chain rule and decompose it like I show here. Basically introducing A first and then introducing B given A. Or I could do it the other way around, introduce B first and then introduce A and B. There is no difference. What this says to us is that for any joint probability distribution, there is a marginal on A and a conditional B given A, that when combined this way, will express a joint probability of any one joint outcome A and B. And similarly, there is a marginal PB and a set of conditionals PA given B that when combined this way will allow you to express the joint probability of any joint outcome A and B. Okay, so this is just a fact. And the way we're going to exploit this fact will matter later on. Sometimes we'll choose to start with one factorization or another, and that will determine what our elementary factors are. But regardless of our choice, we can always reach the other. We can always re-express the factors, recombine them, and obtain the other factorization. This is a very nice result that we're going to be exploiting later in the course, in the class. We're going to do some probabilistic inference and figure out, for example, a marginal where, in fact, in our elementary factorization, we didn't have it. Probability calculus will help us with that. chain rule applies to more variables. It's basically a generalization where you are iteratively introducing variables that are there in the joint distribution. And each time you introduce one, you condition on the ones that have already been introduced. So if I have a joint distribution over three variables, I might start with this PA and then introduce B given A and then introduce C given A and B. I might have chosen a different way to introduce the random variables. And you can guess that there are other ways to factorize this because I could start from C, for example. Now, you might have noticed one thing. When you apply chain rule, our probability factors are growing in complexity. So on the left here, you have a factor that ties together three variables. It's a probability that puts together three variables. It depends on the assignments of three variables jointly. You start with one variable, eventually you have two. At one point, you have all three. So when you apply chain rule and you make no simplifications, you are not actually making your life necessarily easier, because at one point, there will be a factor that ties together all of your variables, and the joint sample space of all those random variables is going to be either exponentially large or infinite or whatever. And that's because chain rule is the chain rule you see on the slide is an identity. The stuff on the right is equal to the stuff on the left. There are no assumptions going on here. Now, to factorize a joint probability like PAB into parts that are simpler, and my notion of simpler corresponds to they involve fewer random variables, such as PA times PB, we need to assume statistical independence of A and B. Right? That's the definition of statistical independence of A and B. Their joint probability distribution, or the joint probability of any joint assignment, factorized like that. An independent assignment for A and an independent probability for B. When independence is licensed only in a specific context, we say it's a conditional independence. So for example, here, if you have the joint probability of A and B given C, and it turns out it's equivalent to A given C times B given C, we have essentially assumed that A is independent of B given C. And this is another way to denote this. Now, conditional independence is a powerful tool, and it's the tool that we are mostly going to exploit. I give you some semantic examples of it here. So for example, to say that one's grade in this course is independent of the weather in November. That's hopefully true. That is essentially an independence of this kind. Right? Suppose A is grade and B is weather. Your grade is independent of the weather in November. So we don't like, well, we would like to believe that teaching staff is not particularly, moody in November, and they shouldn't affect your grade, or independently of how moody they are, your grade should be safe. To say that the number of students and the identity of the teaching staff, so how many of you we have and who we are independent of one another, given that you know the course syllabus, or for example, you know the data knows ID of this course. So how many students join a class, hopefully, do not depend on who is teaching the class. It depends simply on what the class is about. Another example, this is more of an NLP example, to say that in an autocomplete application, the next word depends on, and by the way, number 2 is precisely conditional independence of this kind. Number 3, to say that in an autocomplete application, the next word depends on the current word, but not on the one before that. And there are many, many, many other examples. These are conditional independencies. Now, sometimes you can motivate those with knowledge of the domain, but many independencies, as we shall see, are not very realistic. They are motivated basically by convenience. The autocomplete example might be a good one. When you're predicting the next word, perhaps you only care about the last 1 or 2 words and not the 10th or 12th word in the history, just because that will lead to some more feasible solution, not because it's necessarily realistic. Maybe natural language is such that what you wrote 5, 6, 7 words ago matters for determining the next thing you might write. But feasibility often and tractability will often be a big consideration, and it will often motivate conditional independences that you might not believe in. Regardless of which probability factors we represent directly, so those are the ones we're going to be storing in a computer program and estimating using statistics and data. Together, these factors do induce a joint distribution over all assignments of your variables. And probability calculus will tell us how to obtain those probability values by recombining the elementary ones. We're going to play with exercises like this later on. And yeah, essentially the same message. While we'll be storing and representing only the elementary ones, we'll be able to, on demand, by spending some computation, obtain any other probability we may ever need. So the ability to factorize and answer probability queries has major applications in NLP and really on all of machine learning. We'll soon be looking into answering conditional probability queries, for example, in NLP about a class. That might be a sentiment level, given a large document. So this is a sequence of tokens. And as we will see, it's not viable to store a table of probabilities for every pair. Actually, my initial slides, I had the example, right? That table would grow forever because there's always going to be a new X, a new document that could be part of that table. So if we just hope to store these probabilities, that's not going to work. But we'll see that by exploiting a certain factorization of the joint distribution over these two variables, we'll be able to re-express a probability of any label given any document, or practically any one document that you can think of. And this will work by recombining probabilities that are stored in relatively small tables. We'll only need some knowledge of conditional independence and some probability calculus to do that. And the framework of choice to do that is probabilistic graphical models. So in a very high level, PGMs are a way to specify probability distributions over complex sample spaces. In this class, we'll concentrate on discrete random variables, but they're not limited to discrete random variables. Sometimes the joint sample space of all variables grows too fast, or is infinite, or it's simply too large for you to represent a joint distribution without simplifications, and then you will turn to PGMs, because PGMs give you a language to precisely encode the simplifications you are after. We start by seeing what's known as the tabular representation of a joint distribution. We start by making no independence assumptions, so I can once again show you the magnitude of the problem, and then we're going to fix it. So that's our tabular representation. So suppose we have 3 random variables here, and suppose they're binary. So this is not contextualized in NLP, just using some abstract random variables A, B, and C. Later we'll have some examples to contextualize this. How do we represent a joint distribution over the 3 variables without making any independence assumptions? And I want you to think of this as using a table to really store the probabilities of the assignments. So essentially, you create a big table. That table lists the joint assignments of the random variables. You will find them here. So these are all joint outcomes that you can have. And, you store the probability values of those outcomes. And you might even already see ways to implement this in a computer program. If you know Python, maybe this is a dictionary. The key is the tuple of assignments. The value is the probability value. There may be other ways without Python dictionaries, of course, but this gives you an idea that the tabular representation really corresponds to sort of something you could imagine in a computer memory. The probability values here are not numeric. I'm not showing you numbers, and it's on purpose. It doesn't really matter, right? It only matters that they are probability values between 0 and 1. And this is a distribution. This is the entire space of joint assignments. So if you sum all of these, you should obtain 1, exactly 1. But what precise values are in there at this point, I would say probably doesn't matter. Maybe I wasn't even the one obtaining these values. I was just given the data structure. So watch out. Where the probabilities will come from, that's a different question. We're going to talk about that in other classes. that's a matter of statistics. How do you use data to obtain good numerical values for probabilities? It's not really a question of how to represent the distribution, in the sense that no matter which probability values you give me, they will fit in that table just fine. So the table is how we are representing the distribution. The challenge in representing the distribution in this format that I constrained you to use, the table, is inherent to the sample space being so big. It's precisely because there are so many rows in that table that there is a challenge here, right? If you would add yet another variable, that table would double size, right? Another binary variable. It doesn't really matter whether the numerical values are fixed by hand or estimated by a computer program. There is already a more fundamental problem, which is we can't even manipulate them. Not with the format that I gave you so far. So here's an exercise. How many probability values does it take to represent a joint distribution over n random variables, where each one can take one of k values? So no longer binary, but k-valued random variables. Again, use a table as we did before, and again, make no independence assumption as we did before. So here you pause the slide and work on the exercise, and I will review the solution shortly. All right, so it takes k to the power of n probability values. If you're not convinced, make a small example. Maybe have k equals 3 and do n equals 3 or 4, and you will see. Essentially, this is the number of rows in your table, and for each row, you're going to have a probability value. So these are the number of probability values. This grows very fast, right? So if you just add one extra random variable, this grows exponentially. So let's see how bad this can get. Let's say that the length, our rows are documents, and our probability values are the probability of our documents. So suppose n is the length of a document, and maybe 30 words is a reasonable length. K is the number of words in English. Let's say that it's about 100,000. That's a very conservative lower bound, most likely. How bad is this? And I would say it's pretty bad. And you might argue, well, but not every document will be seen. You won't see every permutation of all words in English. And I'll grant you that. That's true. You can find a sparse data structure that will be more compressed than this, but you're not addressing the fundamental challenge that you are left with the task of, in a way or another, representing these many probability values. Okay. So a quick word on graphs, because they're going to help us. Now that we agree that a tabular representation of a joint distribution can get ridiculously large, we're going to talk about ways to implicitly express all the entries in the table, but only via manipulation of smaller tables. We need a bit of graphs and a bit of probability calculus. So let's start with a direct graphical model or a Bayesian network. I'm not going to talk about the history of why I'm actually not sure I'm familiar with why they are called Bayesian networks. They are neither Bayesian nor particularly networky, if you ask me. There is really nothing Bayesian about them. Throughout this course, I don't think you will see a single instance of a Bayesian model, and they still might be built on direct graphical models. And don't let the word network mislead you. This has nothing to do with the neural network, if you have seen neural networks before. So take it for what it is and for what I present in this slide. So Bayesian network, or I'm still going to use the terminology, okay? Or a directed graphical model is a directed acyclic graph, or a DAG. I might use these 3 words exchangeably. Where the nodes, they represent the circles, they represent random variables. The content of the node, the letter inside, is the assignment of the corresponding random variable, right? So hopefully it's unambiguous that I have a random variable big A, big B, big C, big D, big E, and big F, and those are the corresponding assignments. The edges represent statistical dependence, and they are directed, meaning that you need to know A in order to know the statistical, to have sufficient statistical information about B. And that's sufficient in the sense that you are only able to assign probability to B if you know an assignment of A. There are no directed cycles, and that's the difference between the DAG, which is the top plot, the top diagram, and the other diagram, which is not a DAG, because it has a directed cycle. If you follow the edges, you will end up returning to a node. This never happens up here. DAGs are there to encode a set of conditional independence statements. A random variable in a DAG is conditionally independent of its known descendants given its parents. That's the semantics of the DAG. Okay, that's the definition of it, of our use of it in directed graphical models. So I have a definition there of descendants for you. The descendants of a node are nodes reachable by paths that begin at that node, and then you follow the edges. The source of the edge is the node. The target of the edge is where the arrow points to. The known descendants are all nodes except, so let's see, the descendants of C are nodes reachable by paths that begin at C. So this is a descendant, this is another, and that's it. The known descendants are all nodes except its descendants. So A, B, and E are nodes that are known descendants from C. And the parents are the known descendants that are directly connected to C. So only B and E. Right? And that's the examples I give you here. Sometimes in the future, you will see graphical models where some of the nodes are not shaded gray. We'll talk about them when they come up, but just as a spoiler, shading the node means you have observed the assignment. You know A is indeed the outcome of the random variable. When it's not shaded, it means you haven't observed it. It might be anything in the sample space of that random variable. Okay, so let's see what we are going to do with this. Well, first of all, an exercise. Please complete a table of relationships for each one of the nodes. List the set of descendants, of non-descendants, and the set of parents of the node. I repeated the definition down here. You can also go back to the slide to see the example. So I'll review the solution in a bit, so please pause the video and work on it. There we go. So let's pick one of them, an interesting one. Let's see. D. D looks interesting. So D, the descendants are only F, is the only thing I can reach from D. The known descendants are therefore a complement, everything else. And it has a single parent, right? So let's see, is there any variable that has multiple parents? Yes, C has multiple parents. So you would see here. Are there any variables that have no parents? Yes, A has no parent, E has no parent, indeed. Right, so just double checking that everything looks correct. Great. These are some more semantic examples of Bayesian networks. So you will see that Bayesian networks made a few assumptions. They code for you a few assumptions. So here we are studying whether students are on time. We consider variables like, is the alarm on? Does it go off in the morning? Does the student oversleep? Is the bus the student takes late or on time? Is the student eventually on time? And no other variable plays a role. So, walking the dog it doesn't play a role. The weather outside doesn't play a role. So there is already an assumption here that these are the only variables that matter. And not only that, they actually matter in a specific way. So we are using our knowledge of the domain to motivate some choices here. So for example, I think that whether or not I oversleep in the morning depends essentially only on my alarm being on. And whether or not I'm on time for a class then depends only on whether I overslept and whether or not the bus was late. Many other things could have played a role, but I'm choosing to ignore those. Here's another example now. Whether or not it's cloudy outside has an effect on determining the probability that the sprinkler goes on, because perhaps this sprinkler has some solar sensor, and it goes on when it's cloudy. And being cloudy also affects the probability that it may be raining on that day. And once you know whether it's the sprinkler is on or off, and you know whether or not it's raining, you no longer need to know whether or not it's cloudy in order to talk about the probability of the grasping wet in the campus. So you see, there is a bit of semantics here and a bit of choices that I make in setting this up. But crucially, we see that by knowing the values of sprinkler and rain, I no longer need to know the value of cloudy in order to talk about the probability of wet grass. So this is a conditional independence statement. Again, because a random variable, if you go back a few slides, you should remember this. A random variable is conditionally independent of its non-descendants given its parents. So let's have a look at that. This random variable is conditionally independent of the non-descendants that are not, well, given the parents. So given the parents, the other non-descendants do not matter. Okay. Conditional independences in Bayesian networks. So consider A, B, and C, and due to chain rule, we could write the identity number 1. So that's just an application of chain rule where I chose to enumerate A first, B next, and C last. But if I were told that the assumptions in this specific DAG hold, then I can simplify the first identity. All right, so here the second identity is just a copy of the first. And I highlight here that this DAG tells me that C is independent of A given B. So this factor simplifies to this factor. Now, whereas the first thing here is an identity no matter what, the second step is only licensed by assumption, by assuming that G holds. Okay, so what we achieved is we looked at this thing and we figured out an elementary decomposition of the probability, joint probability on the left into probability factors on the right. They are elementary in that they are the minimum, they reflect the conditional independence assumptions in G. All right. I can state a general result, which is a version of chain rule, is the chain rule for Bayesian networks. So it's chain rule where you simplify all the factors that are licensed by the particular Bayesian network you have. So how does it work? If chain rule functions more or less like what is exactly what we show in equation 4, right? For a given order of my variables, I enumerate them one at a time, always conditioning on all variables that I have already generated. That's what I mean by this notation here. I explain it down here. It's a sequence of variates up until the ith, but not including the ith. When I have knowledge of a specific Bayesian network that I assume to be to govern my problem, to describe my problem, then suddenly for each variable that I introduce, I only need knowledge of its parents. So this simplifies the conditioning context because the parents of the random variable is going to be a subset of all random variables. Okay, so that's the chain rule for Bayesian networks. And you can see what I said before. When you just apply chain rule, eventually you have a factor that ties together all random variables. The last factor in here is going to be xm given all variables up until xm. That's not true here. Here, the complexity of the factor, the number of random variables that the factor clicks together or ties together, is going to be capped by the number of parents, by the maximum number of parents that a variable may have in the Bayesian network, in the DAG. Okay, so that's the general result. We're going to use a bit of it for some exercise. So for each random variable here, conditioned on assignments of its parents in the BN, we will need a conditional probability distribution, a CPD. So, oh, sorry, this is, I skipped the type. This is how we represent now a probability distribution that is compatible with a given BN that we're given. So for each random variable in the graph, so we look at the graph, at the DAG, condition on the assignments of its parents, we need a conditional probability distribution for the possible outcomes of that random variable. And we're going to represent those CPDs. CPD is my shorthand for conditional probability distribution. We're going to represent them in tabular form. So for this graphical model we have, and I'm telling you the binaries are, the random variables are binary. So we have one CPD over A, big A. It's conditional in a silly sense that it conditions on nothing, right? But you have one probability distribution over A, so that's BA. So you're going to need a table for that. For B, well, for B, for the random variable B, you're going to need to condition on the assignment of its parent. So you're going to have two CPDs because the parent may be assigned a 0, the parent may be assigned a 1, since the variable is binary. So two conditional probability distributions. For the random variable C, same story. It conditions on one parent. So the assignments of that one parent is either 0 or 1. So again, you're going to need two CPDs, PC given B0 and PC given B1. So for this Bayesian network, list all CPDs in tabular form. So please pause the video, work on the exercise. I'll review the solution in a few seconds. There you go. So we have a CPD for PA. It is a table with rows that enumerate the assignments of the relevant random variables. It's only one. And those rows contain the probability of each one of the assignments. So we need two probability values to represent this one. In some textbooks, you're going to say, oh, you're going to see that there's a claim you only need one probability value. And I will explain what they're thinking about. The point is that these numbers are constrained to adding to 1. So if you know all but 1, you can figure out the last. Okay, but I think this is a little bit too much for the level of detail we need here. It's sufficient to say we need two probability values. In this other table, we have two CPDs, one when A is 0, one when A is 1, and it's the CPDs for B given A. And similarly, this CPD would add to 1, and this CPD would add to 1. And here we need, well, twice 2 times, so 4 probability values to specify all CPDs of the kind B given A. And finally, for the last one, the set of CPDs of the kind C given B, again, B can be 0 or 1, C can be 0 or 1. Then you get 2 probability values per table. And again, we have 4 probability values. Right, so we would need 10 probability values to specify all of our CPDs for the Bayesian network in this diagram. Right. This might not look like you saved a lot, but we're going to get to an exercise where you're going to see you saved a lot. Now, what happens if A is binary, B is 3-valued, and C is 4-valued? This is the Bayesian network, list the CPDs, just like we did before. So pause the video, work on the solution, and I'll review the solution in a moment. Okay, so the tables just grow a bit longer, right? And the first table is the same. We have one random variable. It doesn't condition on anything, and it has 2 assignments, so 2 probability values. The other table grew a bit taller because now we still can condition only on 2 possible outcomes of A. A is still binary, but B itself now is 3-valued, so it has more outcomes in its sample space. So each one of these CPDs sum to 1, of course. And now we need 2 CPDs times 3 probabilities each, 6 probability values. For the last one, well, C conditions on B, and B now is 3 valued. So now we actually grew the table by adding a CPD to it, right? We have an extra CPD that we didn't have before, which is when B is 2. And C is 4 valued. So we also, for each one of the 3 CPDs, we also have more rows in it. And again, each one of them will independently add up to 1. And now we have 3 CPDs of the kind C given B times 4 probability values for each one of the conditionals. And that gives you 12 probability values. Okay, so you see that we are coding these tables. We see that we can read from the diagram, we can read the shape of the tables, and we are not able to read from the diagram what the probability values are. We're only representing this object. We don't care about what the numerical values are, at least not for now. They will come from some other procedure that we're going to learn in the course. Now let's see the Bayesian network making a bigger impact in our lives. So consider a joint distribution over 6 binary random variables. Without making conditional independence assumptions, what's the size of a tabular representation of such a joint distribution? So take a moment to think about it, pause the video, work on the solution. I'm going to reveal it shortly. Right, so we have 6 variables. We make no conditional independences. So the best we can do is enumerate their joint assignments. They are all binary. So there are 2 to the power of 6 joint assignments. So we need 2 to the power of 6 probability values. That's a lot. Imagine that if you add another variable, it will double. Another variable, it will double again. Now we decide to make the conditional independences that I stated in the following Bayesian network. What is the cost of a tabular representation of the joint distribution? So we're going to have to figure out the tabular representation. Now there are some assumptions in the graph, so we need to use them. We're better off using them. And then we can count how many probability values we need. So pause the video, take a moment to work on this. I'll review the solution shortly. Okay, so what we get? Well, we have A doesn't have a parent, so it's just a table for the assignments of A, and we have 2 probabilities here because we have 2 assignments. B has a parent, which is A. A is binary, so we have 2 CPDs of the kind B given A. B is itself binary, so 2 CPDs with 2 outcomes, that's 4 probability values. And C has 2 parents, 2 binary parents. So the joint assignments of the parents are 4 possibilities. So we have 4 CPDs of the kind C given B and E. C is itself binary, so each CPD will need 2 probability values, 1 for each outcome. So we have 2 times 4, 8 probability values here. D has a single parent, which is binary. So 2 CPDs of the kind D given C. D is itself a binary variable. So 2 possible outcomes. That makes 2 times 2 equals 4. And E doesn't have parents. E is binary, so we need 1 probability distribution with 2 probability values in it. And F has 1 parent, and they're both binary, so 2 CPDs, 2 outcomes in each CPD, 4 parameters. And if I didn't miss anything, we have basically 10, 12, 16, 24 parameters. Yes, 24 parameters, no, sorry, 24 probability values, which is an improvement compared to 64. So this is what we achieve. This is essentially what we achieve. Okay? We still express a joint distribution over this exact same sample space, the sample space of all 64 assignments of A, B, C, D, E, F. So all 64 assignments are in the space, but we don't need 64 probability values to obtain all probabilities of interest. That's what we gain. So let's do a bit of a minimal factorization, and later we do a little bit of probability calculus, meaning we're going to use those fewer probability values that we do know or we do have in the representation to figure out probability values that we do not have explicitly stored in any table. So let's write down the minimal factorization for the three DAGs that I show on the slide. Pause the video, work on the solution, and I'll reveal it shortly. So there we have it. The first one, well, I always advise start with the nodes that have no parents. It's typically the easiest thing to do, and then work your way through the graph. So you have here a PC, it has no parent, and then you can introduce A and B, and they are independent of one another given C. So PAC, PA given C, and PB given C. Another strategy is to just go in whatever order you like and apply the result, the chain rule for Bayesian networks that I showed you before. So let's try that one perhaps. Let's use this one. So PA, it's conditionally independent of its non-descendant given its parents. Well, it doesn't have a parent, so PA. C is conditionally independent of its non-descendants. So these are the non-descendants given the parents. So you will see that you get a term PC given A and B. And B, well, again, non-descendants given parents. It doesn't have parents, so you just get a PB. And then you can figure out this one. Maybe I can do one. Non-descendants A, given, well, let's get a more interesting one. D. Non-descendants is A, B, C. Parents is B and C. So it's going to be independent of A given B and C. And we should have a factor like that. Yes. D is no longer dependent on A because we have access to B and C. Yeah, so it's relatively, you get, with a little bit of exercise, if you exercise a little bit, you get a handle of it. It's relatively straightforward to look at the graph and figure out what the elementary factors are. Once you know the elementary factors, you know their types. The subscripts are kind of like they're telling you what the types are. And if you inspect the types of variables you have, you will figure out the size of those tables. Now, the first big thing is what I told you. It gets more compact. The next big thing is you can still assess all of the probabilities that you would have access to if you had a big table. And this is a matter of probabilistic inference. So for example, here, when we look at this, we know we have tables for PA, PB given A, and PC given B. These are the only tables we will have in the representation. So queries about these three sets of tables are sort of easy because we just look up the relevant role in the relevant table. How about queries that are not about these three things? For example, a query about PB or PC, or a conditional that you don't have access to, like PC given A or PA given C. So all these are possible queries one may be interested in. And probability calculus gives you a way to get to all of them. We're going to do an exercise now, not an exercise, sorry, we're going to do an example together. It all starts with joint distribution. So remember the BN is coding a set of assumptions, conditional independence statements. So you can always look at the BN and start by figuring out how the probability of any joint assignment decomposes in terms of elementary factors. Now, if you have to answer a query about any other outcome, any other combination of recombination of these variables, like a conditional or a marginal, then we're going to be looking up the corresponding, sorry, I lost a bit of the narrative here. If all you're looking for is a joint, the probability of a joint outcome, you just simply read up the values, the relevant values, and multiply them together. The problem, not the problem, but it gets slightly more intricate when the query is not expressed in terms of the joint distribution, but some other combination of A, B, and C, or subsets of A, B, and C. Let's see what we do. For example, here, knowing that we have these three representations, these three tables available to us, so these are the elementary factors, right? Any probability that is not from one of these tables is not to be regarded as elementary, then it needs to be inferred. Characterize a probability from the distribution, a probability for an outcome of B given an outcome of C. So let's see how we would do that. Let's try to compute this for A outcome B, some outcome B, condition on some outcome C. So we start with the definition of conditional probability because that we know from probability theory alone. If you're looking for this conditional, well, you can derive it, you can infer it by combining a joint probability with a marginal probability in this fashion. So it's just a definition of conditional probability. Well, joint BC is not an elementary factor. Marginal PC is not an elementary factor. So I progressed, but I haven't solved the problem yet. So let's keep on rewriting this expression until we have elementary factors in it. So for example, anywhere you see a subset of the variables, you can think of this as a marginal of a distribution that has more variables, right? So a distribution over B and C is a marginal of the distribution over A, B, and C. And I write down the marginal in the numerator. Now, this still doesn't give me an elementary factor, but it helps me in that this is a joint distribution. And I know how to express it in terms of elementary factors. The BN tells me how to do it. Now I can factorize the numerator, the joint probability in the numerator, using the elementary factors from the DAG. That's what I did. And this is great because these are actual numbers I know how to read off of my tables, because I actually have tables for those numbers. That's very good. The numerator is essentially solved. I still don't really have a probability value for PC, not stored in a table anyway. So I still need to do some more work. I'll rearrange the terms for convenience. This is entirely optional. It doesn't change the result, of course, but I noticed here that this term doesn't depend on A, so I can factorize it out of the sum. That's what I did. And now let's work on the denominator, basically. So we stop here. I just copied from the previous slide, and now we're going to concentrate on the denominator. Well, the denominator is a probability involving a subset of the variables in the joint distribution. So again, always the same trick. Start from the joint distribution and marginalize the things that are not appearing on the left-hand side. So now the marginalization goes over two spaces, the spaces of A's and the space of B's. Now that you have a joint probability, you can use the elementary factors in the DAG. So remember, these are elementary. I can read their values for any A, B, C that I happen to be interested in. And again, I'm rearranging things, but it doesn't matter because the result is numerically exactly the same. But I noticed that PA doesn't depend on B, so I factor it out of the sum. Now, if I just substitute this back up here, I get the expression, the final expression. So you see, you can, for any given B and C, you can compute the conditional B given C, even though it's not stored in a table. How do you do that? Well, you express everything in terms of the quantities that are stored in the table. And you do that by exploiting a chain rule, conditional independencies in the DAG, and marginalization, and occasionally also conditional probability. There we go. So it's a bit tedious, yes, but you know, you don't do it very often. Sometimes you need to do for certain quantities you need to predict or compute. We're going to see a very clear case in text classification where we need to use the formula very similar to this one to compute the probability of a label for a given document. It's also quite cool that there is software that does that for you. Much like you can code your neural network and software will deal with the forward and the backward, there is software for you to code your graphical model. And when you give some values of outcomes of interest, it can figure out the necessary algebra to get to the probability value. So here's an exercise. Using the same Bayesian network as before, give expressions for the probability of an outcome in any of the following marginals and conditionals. So find the probability, find an expression for some outcome of PB, some outcome of C, and so on and so forth. Okay. This is going to be a bit tedious, but it's going to give you an opportunity to practice with conditional, marginals, chain rule, and conditional independencies. And once you manage to express a certain composite quantity, like, I don't know, PC, don't bother rewriting it. I can tell you know how to rewrite PC in terms of elementary factors. If it will appear again in the derivation of some other quantity, don't bother expanding. It's clear that you can do it. Okay, so what next? I don't have a solution to this, but if you post solutions to this, myself or the TAs can review if you post them on Canvas. What next? We're going to apply this knowledge, design all sorts of things, text classifiers, language models, taggers, sequence labelers, syntactic parsers, and more. If you're an NLP1 student, then the next slide is for you. It's an exercise on naive-Bayes classifiers. You've already seen the NBC, but now you will give it a PGM treatment. So it's going to help you connect this theory to the content that you were presented to last class. If you're NTMI students, you can totally ignore the next slide and exercise because the model and application that is covered in this slide is going to be very carefully discussed in class and also in our lecture notes, which I link here in any case. You can always go ahead and check, of course, but you don't have to because we'll cover this in a lot of detail in class. All right, so I'm not going to discuss the exercise. You will check here. Oh, I spoiled. I hope you didn't go that far in the video. If you're an LP1 student, have a look at the slides. If you have questions, again, don't hesitate to contact me or the TAs. If not through Canvas, through some other way, some other mean. That's it. See you in class.